Swayam Prabha. Digital India. Educated India.
Good day everyone. Today is the 12th lecture of the course Texture in Materials, and we will do 3-dimensional texture analysis. The concepts that will be covered in this course lecture will be orientation, location, space and misorientation. Second, transformation of crystal coordinate system into orthonormal, which is required to relate it with the sample coordinate system in order to obtain the texture. Third, orientation matrices and Miller indices, pole figure and inverse pole figures relationship with the orientation matrix. So, you see, in order to obtain a complete description of the orientation in a polycrystalline material, it has to be described in terms of 6-dimensional space, and this is basically known as the orientation location space. And the orientation location space consists of a function of 6 variables, and these 6 variables are basically phi 1, phi 2, x 1, x 2 and x 3. So, phi 1, phi 2 are the angular variables, and x 1, x 2 and x 3 are the locations. So, you see that if we have a polycrystalline material as shown in the example below, the schematic below, it has a number of grains and each grain has a different orientation, and in these grains there may be some orientation which might be present in a larger intensity or larger fraction. So, you see that these grains which have the similar kind of orientation are spatially separated out, but will come as an higher intensity while we will do a texture analysis, right, a texture measurement, right. So, you see that what do you mean by the orientation location space? Say for example, if we take this particular plate or sheet metal with sample reference direction x as r d, y as t d and z as n d, and say for example, these are the most important sample reference directions. So, if we have the information of each point or each pixel that is possible, the smallest pixel possible within this whole microstructure. So, if we have an information from here, from here, from here, and if we go like that, raster the whole microstructure and get information from the whole microstructure, then not only we get the information of the texture in terms of phi 1, phi 2 from each of this pixel, but we also get the information of the x and y. On the other hand, if we do a 3-dimensional texture analysis by using, say for example, electron backscatter diffraction in a scanning electron microscope like this, and then we do an ion beam milling so that we can dig a little deeper into the surface and do another electron backscatter diffraction and dig and do another electron backscatter diffraction, so that we obtain the information from the z axis inside the sample. So, x, y and z or x 1, x 2 and x 3 information. So, we have from each pixel phi 1, phi 2, x 1, x 2 and x 3, and thereby we get not only the information about the whole texture of the material, information of the texture at each and every point possible, and also the difference in the orientation or the difference in the texture between each pixel point, which will lead for us to know the misorientation of the geometrically necessary boundaries, grain boundaries, etc. Now, you see, in a material which is processed by some way, right, like solidification, deformation, there may be heterogeneity present in the material, right. So, you see the texture is different in different volume elements of the material, right. Also, it will be different in different positions of the material. So, what happens that in that case one has to distinguish this orientation location space, that is F, in terms of orientation G and in terms of the position of it, that is x 1, x 2 and x 3. So, you see orientation location space which is F times function of G and R, where G is related to phi 1 phi phi 2 and R is related to x 1 x 2 and x 3, is basically related to obtain the local texture, because such kind of information can be obtained only from a very small space, right. And using an FIB one can go below the surface and obtain the information from a small volume of the material. But the texture obtained from this volume of the material is basically known as the local texture, whereas the information from the whole material or a large sample area of the material is known as the global texture. So, you see that what I mean to say here is that both local texture and global texture information is important, but local texture includes the information of the orientation location space in 6 dimension, where one can get the information of the orientation, also the misorientation, whereas global texture, which is obtained usually by X-ray diffraction method, by using normal X-rays produced in the laboratories or from the synchrotron X-rays or from neutron diffraction method, we can obtain the information from deeper in the material, from a larger area in the material, and this could lead to the overall information of the sample. So, there could be a difference in the texture obtained by the global texture method and the texture obtained by the local texture method. Now, you see that if we go into more deep into the definition of the texture. Now, if we say that that there is a material with a number of grains present in it, and each of these grains will have certain orientation, and the sample reference direction x 1, x 2 and x 3 or x, y and z are r d, t d and n d, then you see that the relationship between the sample reference system C s, I have said C s, and the crystal reference system C c is given by the orientation space, which is basically G, and G is basically known as the orientation space or the orientation matrix, and this gives the information of the texture, right. On the other hand, if you see that if we obtain the information in terms of orientation location space, then one can obtain the information between the two grains, right, the orientation difference between the two grains. So, if we have the crystal reference system for the grain C 1 and the crystal reference system for the grain C 2, then we can get delta G, which is basically the orientation difference between the two grains or the mismatch of the orientation of the two grains. So, delta G is basically known as the misorientation, right, that is the texture of the grain boundary. In this type of case, we can obtain the grain boundary texture between C 2 and C 3, that is the adjacent grain, and even if there is orientation difference in a single grain, then there would be a misorientation which may form because of the formation of the low angle boundaries, basically which is agglomeration of dislocations leading to form geometrically necessary boundaries, right. So, you see, when we measure texture, and as we said, the texture is basically the relationship between the sample coordinate system and the crystal coordinate system, and we see that the sample coordinate system, that is, you see here the axis of the sample coordinate system S 1, S 2 and S 3, right, C s equal to S 1, S 2 and S 3, which in most of the case we used a rolled sample or a material which has been rolled, right. So, we use S 1 is equal to rolling direction, that is R d, S 2 is equal to transverse direction, that is T d, and S 3 as the normal direction, that is N d. And these three important sample excesses are actually orthonormal to each other, right. So, they are at 90 degrees to each other. Now, in case of cubic crystals, you see the crystal coordinate system C C, C 1, C 2 and C 3, which is C 1 is equal to 1 0 0, C 2 0 1 0 and C 3 0 0 1. Here is the schematic of it, and this is also in the orthonormal system. So, it is very easy for to find out the value of the G, which is the orientation matrix relating the sample reference system, which is orthonormal, to the crystal reference system, which is again an orthonormal, right. Now, in case of you see hexagonal and trigonal symmetric crystals, what happens is that, for example, a nice example of hexagonal system I will give, that this is a hexagonal unit cell, and you see that if we keep x as 1 0 1 bar 0, then in order to make it orthonormal, the y becomes 1 bar 2 1 bar 0, right, and z is basically 0 0 2. So, you see here the hexagonal system, which follows the Miller-Bevé indices, has the a axes, that is 1 1 2 bar 0 axes at 120 degrees to each other, and we need to convert that into an orthonormal system, crystal system, so that one can relate it to find with the sample coordinate system to get the value of G. So, you see that either you have to use x as 1 0 1 bar 0 and y as 1 2 bar 1 bar 2 1 bar 0, or we have to use 2 bar 2 1 bar 1 bar 0 and 0 1 1 bar 0 with the z, which is 0 0 2, making it 90 90 and 90 degrees. See, therefore, we have for the hexagonal closed packed system two different crystal specimen axes, where x and y can be interchanged, and so while we relate the hexagonal crystal system with the sample, we have to initially denote that what is x and what is y, right. Otherwise, the results coming from different sources, different researchers or different scientists will not match and may create a confusion, right. So, you see that because as I said that the relationship of the sample coordinate system and the crystal coordinate system is given by the value G, which is the orientation matrix, and we usually use that C C is equal to orientation matrix G in terms of C S, which is the sample coordinate system. Now, you see subsequently, you see if any crystal does not have the orthonormal crystal system, that is its lattice parameter are equal and the angle between the lattice parameter is equal to 90 degree, then it has to be made orthonormal and it has to be normalized to the same length. So, you see if we take a triclinic system, where you see you have to see the schematic, where A, B and C are not of equal length, and then the angles between them alpha, beta and gamma are also not equal angles, right. Now, this has to be converted into orthonormal system with lattice parameter equal, that is the normalized to the same length, and the angles has to be 90 degrees. So, if we superimpose a lattice parameter is a orthonormal crystal system 1 0 0, 0 1 0 and 0 0 1, then we find out that we can superimpose it in such a way such that the A coincides with the 1 0 0. Then there will be a difference in the the excess 0 1 0 with B C and 0 0 1 also with the B and C, and this is given in the figure, which is self explanatory, right. So, if we find out the relationship matrices between this ABC and 1 0 0 0 1 0 and 0 0 1, which is why it is like this, because it is normalized to a unit length. So, we obtain the value, there will be 6 values of this matrix, and let us say these are L11, L12, L13, L21, L22, L23, L31, L32, L33. So, you see that L11 is basically equal to A, because it lies along the same direction as the A, whereas L12, that is the relationship of 1 0 0 with respect to this B vector, is basically equal to B times cos of gamma, because this is the angle between 1 0 0 and B, whereas L13 is the relationship between 1 0 0 and the C, which will be B times cos of beta. Now, L21 is equal to relationship between 0 1 0 and A, which is A cos of 90 degree, and so it becomes 0. L22 becomes B of sine of gamma, right. L23 becomes a relationship, a little complex relationship, C times cos of alpha minus cos of beta cos of gamma divided by sine of gamma, right. Whereas, you see L31, which is between 0 0 1 and alpha, is again and A, which is again A times cos of 90 degrees is 0. L32, which is again B times cos of 90 degree is 0, and L33 is equal to C times, you see, 1 plus 2 cos alpha cos beta cos gamma minus cos square alpha minus cos square beta minus cos square gamma to the power half by sine of gamma, and this can be calculated and is given in a very old work by Young and Lighton, which has been published in 1972. So, you see that using this matrices containing this 9 variables L11, L12, L13 to L33, we can obtain that for orthorhombic crystals the L is equal to A, B and C in the diagonals, rest all are 0, because you see in the orthorhombic crystals A is not equal to B, is not equal to C, rest alpha, beta and gamma is 90 degrees. In case of hexagonal crystals, L becomes equal to L11 becomes A, whereas L12 is equal to minus A by 2, L13 is 0, and you see L21 is 0, L22 is A root 3 by 2, L23 is 0, L31 and L32 will be 0 as we found out, and you see L33 is basically equal to C, because C is at 90 degrees to both 112 bar 0 and 101 bar 0 of the hexagonal close packed system. Now, this is how we use the Young and Lighton's method to convert the different crystal systems, non orthonormal crystal systems into orthonormal crystal systems, so that the relationship C C is equal to G times C S could be obtained between two orthonormal systems, right. So, the relationship between the texture could be obtained. So, you see that what is an orientation matrix? As I said that the relationship between the sample coordinate system and the crystal coordinate system, angular relationship, is the orientation matrix, and it is given by C C is equal to G times C S. So, if we look into a schematic like this, to find out orientation matrix, let us say that there is a specimen which has a rolling direction coming out of the screen, and then on the right side it is T D and vertically it is N D. So, x, y and z, the important sample reference direction R D, T D and N D are at 90 degrees to each other like this. Say for example, this is a polycrystalline material and there are a number of grains in it, and many grains are having different orientations or different texture, but say of grain is present with this kind of a texture, right. So, the unit cell is oriented in this manner. So, you see the important crystal reference directions for this kind of orientation or this unit cell can be given by 1 0 0 in this direction, 0 1 0 in this direction, 0 0 1 in this direction, right. So, now you see that the orientation matrix is basically the mathematical tool for calculation of all the description of the orientation. You see that how it is so, it is because you see if G is the orientation matrix, then the relationship of 100 with respect to x is basically cos of alpha 1, because the angle between x and 100 is alpha 1, right. On the other hand, the relationship between y and 100, that is T d and 100 is beta 1. So, it is cos of beta 1. So, you see the relationship can be given from in the G 11, which is cos of alpha 1 is the relationship between R d and 100, cos beta 1 is the relationship between T d and 100, cos gamma 1, right, that is the angle between the N d and 100, that is the relation here G 13 is equal to cos of gamma 1. Like that, the relationship between 010 with R d, T d and N d is cos alpha 2, cos beta 2, cos gamma 2. On the other hand, the relationship between 001 with respect to R d, T d and N d is cos alpha 3, cos beta 3 and cos gamma 3, right. So, G is an orientation matrix consists of 9 variables G 11, G 12, G 13, G 21, G 22, G 23, G 31, G 32, G 33, that is the angle, the cosine of the angle between the crystal coordinate systems and the sample coordinate system, and that is basically you see we have the here in the horizontal the 100 axis is constant for the first where I am pointing out. In the second one 010 is constantly related with R d, T d and N d. In the third one 001 is related to R d, T d and N d. So, here 100 is related to R d, T d and N d and the rest as I said so. So, if we look closely into the orientation matrix, that is the G matrix, we can find out that if there is a sample consists of many orientations or few orientations, or you see like this 4 kind of orientation, then each of this orientation will have a orientation matrix, right, and then each of this orientation because as I said that G, that which is cos alpha 1, cos beta 1, cos gamma 1 is the relationship between 100 with R d, T d and N d, and like that 010 with R d, T d and N d, 001 with R d, T d and N d. The G matrix can be written in terms of U, V and W divided by N 1, where N 1 is basically root square of U square plus V square plus W square, and this U, V and W is basically the Miller indices of the R d, right, whereas Q R S divided by Q R S, Q divided by root square of Q square plus R square plus S square, R divided by Q square root of Q square plus R square plus S square, S divided by root of Q square plus R square plus S square is basically the cos alpha, cos beta 1, cos beta 2, cos beta 3, that is the relationship of 100, 010, 001 with T d, right. So, this gives the Miller indices of T d, whereas HKL is the relationship of 100, 010, 001 with N d. So, you see from the cos alpha 1, beta 1, gamma 1, alpha 2, beta 2, gamma 2, alpha 3, beta 3, gamma 3, one can decipher the HKL, UVW pertaining and QRS pertaining to N d, R d and T d, and one can cross check this whether this relation is coming correct by you see T d is basically equal to N d cross R d, and so the QRS here must match the QRS by doing the cross product of it. So, you see that here I will give you a disclaimer that it is generally only for the cubic materials that the indices of the planes and the directions are identical. So, in case of other material like hexagonal crystal system or trigonal system, the planes and the direction are the planes and the perpendicular directions are not identical, right, and hence it is less straightforward. In case of non cubic materials, means that is with non-cubic symmetries to extract the ideal orientation from the orientation matrix, like we have done it here, and this is only for the cubic crystals. So, one should remember that this relationship of the orientation matrix with the HK, LVW and QRS, that is the important sample reference direction in terms of crystal orientation, is basically for the cubic system, and for the non-cubic system it becomes a little complex. So, you see finally, if we try to relate the pole figure, which we have shown is one way of measuring texture with respect to the orientation matrix, and there has to be a relationship, because you see a texture when calculated from a certain processed material, the texture shown in terms of pole figure or in terms of inverse pole figure should match with the Miller indices, and it should be equal to the orientation matrix. So, what is the mathematical relationship between the pole figure and the orientation matrix? This has to be known, right. So, you see if we talk about the pole figure, and if we look into this figure, this is a 3-dimensional sphere which has been shown, and this is the stereographic projections 2 dimension of this 3-dimensional sphere. So, you see that if we have shown this by a hexagonal unit cell, because it is easier to distinguish between different planes when we look into the hexagonal unit cell, and say for example, the hexagonal unit cell has an important axis which is basically the c axis, say this is r, and this r is at an angle alpha, right, from the important pole which is the ND, and sometimes it is also called the north pole. So, if it is at an angle alpha from the north pole, and this is this alpha is described as an azimuth of the pole. So, at ND or at the north pole, alpha is basically 0 for this unit sphere, right, and say that the angle beta is basically the rotation of this pole about the RD, and which is basically this one. So, the angle beta characterizes the rotation of the pole around this north pole, which is the polar axis, starting from the specified reference direction, that is an important reference direction, which is basically RD. So, RD is the most important reference direction, and the angle beta can be given by this. So, this can be also shown for a cubic crystal, and this has been shown when we are looking to the stereographic projection from ND, and if we are looking from ND, then you see that there is an important pole which is this one 100, any one of these 3 100, and which is at an angle alpha from ND, and then it is about a beta rotated from the important sample reference direction RD. So, you see that if R is a vector parallel to the pole of interest, like this is 001, 0001, and this is 100, that is some plane, say xyz plane or xyz pole, then it can be expressed in terms of 2 frames of references, that is the sample frame of reference which is CS and the crystal frame of reference which is CC, right. So, let us express this R in terms of sample frame of reference. So, R is basically equal to S1, right. Let us say this is S1, and S1 times, you see this is alpha. So, this is sine of alpha which comes out to be here, and then you see cos of beta which comes out to be here. So, in terms of S1 we have described R, and plus S2 which is basically you see between the transverse direction, some transverse direction here, right, TD, which is 90 degrees to RD and ND. So, it will be sine of alpha, and then it will be basically sine of beta, right. Now, if this is sine of beta, then plus S3 which is with ND, and that is S3 cos of alpha. So, R is equal to S1 sin alpha cos beta plus S2 sin alpha sin beta plus S3 cos alpha. That is in terms of the sample reference system, and in terms of the crystal reference system, it is 1 by root of the xyz, that is the Miller indices of that pole, that is root of x square plus y square plus z square times C1 x plus C 2 y plus C 3 z, right. So, the crystal coordinate system C 1, C 2 and C 3 with respect to x, y and z, which is the Miller indices for the particular pole of interest with respect to this R d, N d and T d. Now, you see, if so, the x, y, z is the coordinate of the pole of the crystal frame. Okay. Now, if we relate this sample reference system with the crystal reference system, we find out that sin alpha cos beta, sin alpha cos beta, sin alpha sin beta, cos alpha is equal to, this is the sample reference system, times the G matrix is equal to the crystal reference system, that is x, y, z, and normalized crystal reference system, that is 1 by n, which is root of x square plus y square plus z square. So, C s is times G is equal to C c. Now, if we are writing this, then it becomes sin alpha cos beta, sin alpha sin beta cos alpha, this is the C s, that is the sample reference system, equal to the C c, which is 1 by n x, y and z, G of inverse, right. So, it is orientation matrices inverse, inverse of the orientation matrix. So, this becomes G 1 1, G 2 1, G 3 1, G 1 2, G 2 2, G 3 2, G 1 3, G 2 3, G 3 3. So, you see the orientation matrix is here in inverse. So, instead of G 1 1, G 1 2 like this, it is G 1 1, G 1 2, G 1 3. So, just remember this. So, you see that we have shown that using the orientation matrix, one can relate the pole figure, the important pole and its angular direction with respect to the important sample reference system with respect to the G matrix, which is the orientation matrix. So, pole figures and orientation matrices are mathematically related. Now, if we look into the inverse pole figure, and as we know that inverse pole figure is an important method to show texture, and and you see in the pole figure we represent the crystal direction with respect to the sample direction. In the inverse pole figure, we represent the sample important sample direction with respect to the crystal direction using one of the triangles from the stereographic projection using the symmetry of the crystal. So, most of the time inverse pole figure are often used when the sample is axially symmetric and where only one axis is means most important. So, if we use the analogy of this equation R equal to sin S 1 sin alpha cos beta plus S 2 sin alpha sin beta plus S 3 cos alpha, where the for the pole figure where alpha and beta are the angles between the unit vector x y z, which is the crystallographic axis in terms of the sample frame of reference. And in this case, in case of the inverse pole figure, one can use two values of angles gamma and delta in a similar manner for the vector of the specimen axis S 1 in the with respect to crystal coordinate system C. So, you see instead of R, you see S, the important sample reference direction, the first one may be say the rolling plane or the rolling direction, or you see in case of extrusion the one singular axis is the extrusion axis. So, say S I is equal to C 1, which is the first important crystal direction times sin gamma cos delta plus C 2 sin gamma sin delta, same as this equation, and C 3 cos gamma, right. So, in this case also the relationship of this crystal coordinate system, in case of pole figure this was the sample coordinate system. So, the relationship of this crystal coordinate system, which is sin gamma cos delta, sin gamma sin it is delta and cos gamma, is equal to, you see the sample reference system x, y and z, x s, y s and z s normalized by 1 by n, whereas n is equal to roots of x s square plus y s square plus z s square, is in relationship with G here. So, C c is equal to C s times G, which is G 1 1, G 1 2, G 1 3, G 2 1, G 2 2, G 2 3, G 3 1, G 3 2, G 3 3. So, G 1 1 is basically cos alpha 1, G 1 2 is cos beta 1, G 1 3 is cos gamma 1, and like this cos of alpha 2, cos of beta 2, cos of gamma 2, cos of alpha 3, cos of beta 3, cos of gamma 3, that is the G matrix is related. So, you see that these expressions basically for the pole figure and the inverse pole figure describes the elements of the orientation matrix G in terms of position of the specimen axis, and for the inverse pole figure, and in terms of the crystal coordinate system in case of the pole figure. So, from this lecture we can conclude that first, orientation location space, which is phi 1, phi 2, x 1, x 2, x 3 can be used to completely describe the microstructural morphology of a polycrystalline material. Orientation, second, orientation is the relationship between the sample and the crystal frame of reference. Misorientation is the relationship between two adjacent crystal frame, and misorientation gives the grain boundary texture, right. So, you see if you have two grains, adjacent grains with two different orientation, the mismatch between the orientation gives delta G, which is basically known as misorientation and is also a form of texture and is known as grain boundary texture. Misorientation matrices can be used to describe the orientation. So, G matrix can be used, it has 9 variables, and so it can be used to describe the orientation and are related to the important sample reference direction in terms of Miller indices. We have shown that how G matrices is related to HKL, UVW and QRS of RD, TD and ND important sample reference system, and then the texture represented by the pole figure and the inverse pole figure are mathematically related to the orientation matrices. So, thank you.